Hello everyone, I'm Mahtal Masumi and I'm currently pursuing my master's degree in Geodesy, which is a fascinating subfield of geomatics engineering. Today, I'm so excited to share with you some fundamental concepts of geodesy and its great significance in understanding our planet. So let's start with a broad perspective and gradually narrow down to the specifics of geodesy. First of all, we will explore the field of engineering as a whole, highlighting its importance in various branches. Then we will focus on geomatics engineering, discussing its objectives and applications, and providing some real-world examples. And finally, we will delve into the specialized field of geodesy. Now I want to start with the definition of engineering. According to the definition of engineering, which is presented by American Council of Engineering Companies, it is a discipline dedicated to problem solving and innovation. It is notable that it's not just about addressing existing challenges, but also about using some scientific principles and creativity to develop new technologies and systems that can make our lives easier and more efficient. We can truly say that our built environment and infrastructure, the devices we use to communicate, and the applications that helps us find our location and routes have all been designed, assembled, or managed by an engineer. So, from satellites to cell membranes, engineers use math and science to achieve extraordinary things and find solutions to some of the world's most complex challenges. On this slide, you can see some images presenting various branches of engineering, such as civil engineering, environmental engineering, electrical engineering, geomatics engineering, which without them our lives would be unimaginable. Now, among the various branches of engineering that we have mentioned just some of them, let's focus on geomatics engineering. So the question is, what exactly is geomatics engineering? There are many definitions of geomatics engineering out there, as you can see in this slide. But I find the easiest one, which would be understandable even for beginners, comes from Calgary University. According to that, geomatics engineering is the surveying of the entire or a part of the earth with various techniques, and the resulting spatial data is processed, evaluated, and expressed in forms of maps, charts, or digital models, enabling us to better understand and manage our environments. The aim of geomatics engineering is to collect, analyze, interpret, and manage spatial data about the Earth's surface and its features. These features can be physical, like mountains, coastlines, forests, or also can be human-made features. Also, they can be land use and land cover. Land use refers to how land is utilized or the way it is used by people. So it can be residential, agricultural, industrial, and so on. Land cover refers to the physical material covering the Earth's surface, so it can be vegetation, bare soil, and water bodies, or something else. Other features can be topography, geological and geophysical characteristics, and even cultural and historical features, which we mention them later. If I want to mention the applications of geomatics engineering, I can say that it has a wide range of applications across various industries because it focuses on spatial data. So anything that deals with spatial data can make use of geomatics. One of the common applications of geomatics is boundary determination. As we know, nowadays lands are becoming increasingly valuable. Even a single square meter can be highly expensive. Accurate boundary determination ensures that property lines are precisely defined, preventing disputes. By way of example, after the BAM earthquake in Iran, many people were unable to locate the precise boundaries of their properties due to the destruction of landmarks. However, with modern global positioning technologies, geomatics experts could accurately determine and restore property boundaries using precise coordinates. Moreover, geomatics can be useful across all stages of disaster management, which can be before, during, and after an event. In the pre-disaster phase, it helps assess risks and predict potential hazards, such as earthquakes, floods, or wildfires. Furthermore, geomatics engineering proves to be useful in urban and regional planning. Spatial analysis tools enable planners to analyze demographic trends, land use patterns, transportation networks, and environmental factors. This data-driven approach supports the development of smart cities. Also, precision agriculture uses geomatics technologies to optimize farming practices. Integrated data from satellites, drones, and ground-based sensors are used to analyze spatial data such as soil characteristics, moisture levels, crop health indicators like NDVI, and weather patterns. Remote sensing data provides real-time monitoring of crop growth and health, enabling early detection of stress factors like pests, diseases, or nutrient deficiencies. This information helps farmers make data-driven decisions on irrigation scheduling, fertilizer application, pest management, and crop rotation. Archaeological mapping using geomatics involves the application of advanced spatial technologies to document, analyze, and preserve archaeological sites and artifacts. Geomatics techniques are employed to map and study archaeological landscapes with precision and detail. In 2018, researchers used LiDAR technology in Guatemala to discover an ancient Mayan civilization previously unknown to archaeologists. The LiDAR data captured detailed images of the dense jungle terrain, revealing hidden architectural remains, roads, and agricultural traces. Such advancements not only aid in preserving cultural heritage but also contribute to unraveling mysteries of ancient civilizations worldwide. Now I'm going to introduce some majors of geomatics engineering. The first one would be geodesy, which involves the measurement and precise mapping of Earth's shape, gravity field, and rotation. Geodesists mainly use techniques like satellite positioning, gravity measurements, astronomical observations, and so on for geodetic surveys and global positioning. The next one, as you can see, is RS, which stands for remote sensing. As its name suggests, it focuses on acquiring and interpreting data from satellites, aircraft, or drones to study Earth's surface and environment. Applications include environmental monitoring, agriculture, urban planning, disaster management, and so on. The next one is GIS, which is the acronym for Geographic Information System. Focuses on the capture, storage, analysis, and visualization of spatial data. GIS professionals develop and maintain databases, create maps, and perform spatial analysis for applications in urban planning, natural resource management, and public health. Next one is photogrammetry. Utilizes aerial and satellite imagery to create accurate 3D models of terrain, buildings, and objects. Engineers in this field apply techniques such as stereo imaging and digital image processing for applications in mapping, urban planning, and infrastructure development. The next one is hydrography, deals with surveying and mapping of water bodies, coastlines, and seabeds. Hydrographers use sonar, LiDAR, and GPS technologies, so we can say they use various technologies to create nautical charts, support marine navigation, and manage coastal zones. And that's it. These are some important majors of geomatics engineering. And there may be other majors of geomatics engineering, but in this slide, I've tried to introduce the most renowned ones. After covering the foundational concepts, we now arrive at the principal slide, which delves into the science of geodesy. This section is informed by insights from the book Geodesy, the Concepts by Petr Vanicek. The first sentence of this book, which is written in the introduction part, is ever since man evolved into a thinking creature, he has been interested in learning about the earth. This shows that our fascination with understanding the earth started from the very beginning. Throughout history, civilizations have held diverse beliefs about the shape of the earth. Some ancient societies, including early Greek philosophers, conceptualized the earth as a flat plane, a perspective often influenced by observations of the horizon and the apparent flatness of large bodies of water. In contrast, figures like Pythagoras believed that the Earth is spherical. They reasoned this based on observations such as the curved shadow of the Earth on the Moon during lunar eclipses and the gradual disappearance of ship's hull first over the horizon. These differing perspectives on the Earth's shape laid the foundation for the evolution of geodesy, inspiring further systematic observations and measurements to understand the Earth's true form. So, by exploring these historical examples of contrasting beliefs about the shape of the Earth, we illustrate one of the most fundamental aspects of geodesy. Geodesy, as a scientific discipline, aims to accurately measure and understand the true shape, size, and orientation of the Earth, encompassing the study of gravitational fields, the Earth's rotation, and the precise positioning of points on its surface. It provides crucial information for navigation, mapping, satellite positioning systems, and a deeper insight into global phenomena such as sea level changes and tectonic plate movements. Now let's turn to the disciplines where geodetic information, positions, and other is needed. Geodesy plays a crucial role in mapping by providing accurate measurements of the Earth's surface and precise geospatial coordinates. For example, control points established through geodetic surveys serve as reference markers for aligning and validating geographic data. Also, in the urban environment, the locations of man's creations, such as underground utilities, must be defined and documented for future reference. During the building of large structures such as dams, bridges, and factories, it is necessary to lay out the various components to these structures in predetermined locations. As well, it is often necessary to know the movements of the ground and water level before, during, and after the construction. Geodesy is crucial for accurately defining and serving boundaries with regions, countries, or properties. By providing precise measurements and coordinates, geodesy helps ensure legal and territorial integrity, resolving disputes and facilitating effective governance and management of land and maritime boundaries. It has been realized in the past few decades that it is necessary to study the effects of human actions on the environment. One such effect is the movement of the ground caused by the removal of underground resources, such as water, oil, and minerals. The detection and monitoring of these movements is a geodetic problem. Also, it has been recognized that the establishment of environmental data banks to serve as integrated information systems should be based on land parcels whose locations are uniquely defined in terms of coordinates. Again, it is advisable that these coordinates be referred to a geodetic network. Moreover, all the positional information needed in geography is provided by geodesy. This information is of a global character that only geodesy can satisfy. Geodesy is essential for hydrography, the science of measuring and mapping bodies of water. Geodetic measurements contribute to safe navigation, marine resource management, coastal zone planning, and environmental conservation efforts worldwide. Finally, here is a brief explanation about the theoretical basis of geodesy. Geodesy relies heavily on mathematical principles to model and understand the shape, size, and gravitational field of the Earth. Key mathematical concepts include spherical geometry, calculus, linear algebra, and statistical methods. These tools are used to develop geodetic models, compute geodetic coordinates, and analyze geodetic data with precision and accuracy. The next one is computer science. Computer science plays a pivotal role in modern geodesy, facilitating complex computations, data analysis, and modeling. Many of the problems faced by geodesy today require a computer solution. Geodesists, like most other scientists, should have an appropriate knowledge of at least one high-level programming language. Because of the large quantities of data involved in most geodetic problems, geodesists should have a proper training in data handling. The next one is physics. Physics is almost as important to a geodesist as is mathematics. Since Newton, gravitation has played a very important role in geodesy. This importance only increased when it was realized that gravity is the geometry of the space in which most geodetic observations are taken. The next one is mechanics. Mechanics is required to understand the motions of the Earth and its satellites. And the last but not the least is astronomy, which has historically been intertwined with geodesy, providing fundamental principles and observational techniques essential for understanding Earth's orientation in space. Astronomical observations, such as those of stars, planets, and celestial bodies, help define reference points for geodetic coordinate systems. These references were used in this presentation on geodesy. For more detailed information, you can refer to these sources. Thank you for joining me on this journey through the fascinating world of geodesy. As we continue to explore Earth's depths and heights, let's remember that every measurement and discovery brings us closer to understanding our place in this universe. Stay tuned for more upcoming presentations on related topics. Have a good day.